6620, go get into something called path analysis, structural equation modeling. And it's a good follow up to factor analysis. And hopefully, in this video, I will explain to you why I feel that way. Um, Motivating example, let's say we'd like to predict success in a calculus course based on different attributes. One thing we may do is we may consider using simple linear regression, where we would have one predictor, and quite possibly we could use some academic measures, ACT, pretest, maybe academic performance in a previous class. Since we know that academic success in general depends on many more factors, we may consider moving into the multiple regression world and predict success in calculus from different academic situational dispositional type of data. Um, Now, but let's pump the brakes a little bit and think about what if success is measured by success in a prerequisite course or courses. So what if we wanted to predict success in a calculus course based on success in college algebra and trigonometry, assuming the non-pre-calculus model, and having a college algebra course leading into a trig course, leading into a um, calculus course. And you can see in this design why just throwing algebra and trig in as predictors when college algebra came before trigonometry may not be appropriate. So, in other words, what if one of our predictors is dependent on one of the other predictors? And one may argue, and I would, that trig success is dependent on success in college algebra. So the goal becomes more complex and appropriate for something called path analysis. Now, the last time I studied path analysis was in, I think, 2000 or 1999. I'm currently posting this video and creating it in 2022. It's been a while. I've never had an entire class on path analysis. I think one class we spent about half the term on it. So it's kind of cool to revisit some of this. But we're not going to dig too deep into the weeds on this. And if I did dig deep into the weeds, I would have to do a lot of extra homework. So anyway, I think of path analysis as an extension of multiple regression, and it's used when a predictor depends, quote unquote, on another predictor. So we may be able to think about modeling the path of success into calculus, or I'm sorry, modeling calculus success as the path into calculus. So college algebra, we could argue that trig success is a function of college algebra, and these two collectively go together to predict calculus. Now, I will tell you, just get on a little bit of a tangent here. This model is only true if the instructional unit is held constant. So if instructor for the college algebra course teaches the same or very similar to the professor for the trig, and the same thing said for calculus, then college algebra trig, that path into calculus is predictive. But if we vary the instructional unit, we find out that success in previous courses is not necessarily predictive of course success. So just a little something for you to maybe think about. First presented, I forget when this was actually the year. I forget the timeline, historical timeline, but it was first presented as a causal modeling. But we find out in statistics that proving causation is extremely problematic. Something I do with all of my undergraduate intro courses, and I even do this with the statistics class I teach to the math majors, is I go into class and I'll go over to the outlet that controls the lighting for for the classroom, and I'll turn the light off, and then I'll turn it back on, and I'll turn it back off. So it gets very annoying. And I'll ask the students, is flipping this light switch causing the light to go on and off? Well, most people will say, well, yeah, obviously it does. So I repeat the question. So flipping the light switch causes the light to go off. And they'll say, well, yeah, it does. We just witnessed that. So what I'll have is I'll have my backpack with me, and I'll have a light switch, and I'll have a light bulb, and I'll give a light switch to one student and a light bulb to another student. And I'll tell the one student, "Well, flip the light switch." And I always joke, and I tell them, if that light bulb comes on, I'm out of here. You guys are on your own. Obviously, the light bulbs. Well, I hope that light bulb doesn't come on, but obviously it's not. And so again, the point of that demonstration is that when we examine a relationship between two occurrences, sometimes it's so easy to inject a causation issue there, a causation association, when the fact of the matter is the light bulb being turned on is dependent of the light switch, but there's a lot more going on behind the scenes, uh, making causation extremely problematic. And we see this all the time. My dad owned tire stores for years, and I'll never will forget one customer who came in, and I think she had like a water pump put on, installed, and then she went out the next day and her battery wouldn't start. Well, she blamed her bad battery on Dad and his team and mechanics putting on a water pump. Well, the fact of the matter is, her uh, uh, battery would have gone dead that day anyway. It didn't happen what happened, before, but she said, "Well, you putting on that water pump caused because it came first, right?" Well, that's a goofy model, but sometimes you can't convince people of that. So a little bit of terminology. First thing, we eliminate independent, dependent terminology, predictor, all that, and we replace with exogenous and endogenous variables. So exogenous variables will have arrows starting from them, but not pointing toward them, and endogenous variables will have at least one arrow pointing toward them in the path model. So in our case, college algebra would be exogenous because it has arrows only pointing out, and trig and calculus would be endogenous variables because they have uh, arrows pointing toward them. Um, so that would be kind of an interesting design. Now, an example, we usually get into more sophisticated. So A through E in this design would be exogenous, F and G, clearly endogenous. The arrow 2G is term. It's a residual, and we usually include that information in our path diagram. Now, what we get into a lot is this is perfect for latent unobserved variables, which are often used as exogenous variables. Because if we think about this design, let's say the G is success in a calculus class, let's just stick with that, and F is success in a trig class. Well, A could be in this model success in college algebra, but then we could have B, C, D, and E, maybe a grit factor, maybe a self-determination, self-motivation, maybe a perseverance factor, maybe D, and maybe E is, I don't know, some self-confidence, some self-esteem, whatever it may be. So often we say that the student comes into, in fact, I think if I were actually setting that up, I would have, if A was college algebra and B, C, D, and E were these unobserved latent variables that emerge from a factor analysis, I would probably have the exogenous variables as B, C, D, and E leading into A, which leads into F, which leads into G. So that's probably the path that I would test if that was the motivation for the study. So anyway, the point is latent variables are often exogenous variables that we want to um, uh, kind of examine the effect of bringing them into the path analysis. Assumptions, pretty straightforward. All variables are assumed to be linearly related. Endogenous variables should be continuous. A lot of people say that if you have ordinal data that as long as you have seven levels. So let's say you wanted to include a Likert scale data in as an endogenous variable. The research that I have seen and that I usually go with is we would need a seven scale Likert scale. So I don't know, strongly disagree and strongly disagree and disagree and no feelings and uh, agree and then strongly agree, whatever that would be. So we'd need seven instead of the typical five that we get. And actually, I've seen literature that says we can proceed with a ordinal variable with five levels. So that's just something you'd have to investigate a little further. We don't include interaction terms. If you have a interaction in the presence of an interaction, then just add a new box as a endogenous or X. There you go. I can't say it. Into your model. And residual should be uncorrelated. In other words, the covariance should be equal to zero. So that's all I've got. We'll dive into a couple of very simple models, and I'll show you how to run this using R. It's kind of fun stuff.